Log on, tune in, find out. Another good idea from Cambridge.
We start our last session before the poster one. I'm going to start by one story. Some 10 years ago, at my department, we tried to organize an excellence center within the framework of a Marie Curie program. Well, as many protests, finally it failed. But before this, before I knew that, I had asked Werner Müller to suggest me some young person to join the center if it would be successful. So he suggested one young bright guy, not known in our community. And after many years, I realized that I narrowly missed the opportunity of collaboration with this young guy whose scientific career was rapidly developing. So this is a bit depressing for me. And as for this guy, you can see him here. This is Milan Stehlik from Slovakia.
Yes. Thank you very much for a very nice introduction. Actually, it's completely true that the Werner is responsible for everything what I'm what I'm telling here, except of errors, which are mine.
Correlated with mine.
Yeah. Well, yes. So properly stating what is this about, it is probably about trying to understand what Werner wants me to make or what he learned me, and I was still not able to understand it because I came a little bit from mathematical background and I made a PhD in Slovakia in a quite different field on Kullback-Leibler divergence relation to the testing. So what I have learned from Werner and then later collaborators, Jesus, Luke, Anatoly, Henry, yeah, clear, and all the younger who are much more bright than me. So for instance, my diploma students like Kiselak and the colleagues like Rado Harman and so on. And not forgetting Andrej Pazman, because I made a basic course on optimal design by Andrej, and this was my only course I made in optimal design. At that time I was a student at Comenius. So thank you very much for invitation of Darius and Andrew Curtis. It's great to be here. I'm learning a lot. I hope I will be able to understand it properly. Good. So what I will be speaking about, I will try to make some small examples and remarks on the modeling of the Gaussian processes. I hope in relation with optimal design. And recently I was thinking about some regularity properties we should have, or we can have, or we might have. So this will be about. So outline of the talk will be some, let us say, mathematical or statistical modeling for stochastic processes with potentially continuous or more complex times. Then I will discuss a little bit on dependent structures, mainly on covariances, how we can model it when we, for instance, have a singularity in the process, which is related mainly to the problems with the covariance matrix. And then I will follow, I have a great opportunity to use many slides of Werner, because we have been working for a very long time together. So trend and covariance parameter issues, and some applications and some open problems. So which design is good for a stochastic processes? That's a difficult question, I think. So one thing that we can plunge in the approaches from a classical setup where we have uncorrelated errors and use a Fisher information matrix and use the well-developed theory and just plug it and try to study the properties. We have been with Werner finding justification of, for instance, for d-optimality or Fisher information based optimalities under correlation, and I think so is worth to have a look on the papers in computational statistics, or mainly in the applied stochastics model in business and industry, where we have listed a couple of paradoxical behavior or some kind of specialities when you have a continuous time. Some of these specialities are really related to the continuous time, to the continuity of the time. And it was observed already by other authors like Smith in Trabajos de Statistica 1961. I will explain later. There are some works where the people try to justify the usage of the d-optimality under correlation. For instance, Passman published 2, Upton Welsh in Canadian Journal of Statistics for special 3 covariance structures, Zuenstein, Zangen, Zimmermann, and so on. So one thing is what probably we can state also from Zuenstein, that we are searching for a monotonic behavior between the two things, and that is the covariance matrix of the ML estimate, the inverse, and the Fisher information. So if we have some monotonic relationship, even not equalities, that we can have some optimality in respect that we can choose what is better. But generally, and we have observed now with Alex Boukovalasis and Dan Cornford by some simulations that general monotonicity is in a more complicated models is observed only with some proportion of situations. So it's not the general case, but in these examples I will be showing actually which kind of behavior we can expect. So when we are speaking about the Fisher information and want to introduce in this setup of stochastic processes, I wanted to point out a couple of things which I considered for me to be most interesting. Actually, the Fisher information itself was not completely introduced by Fisher, because there is a paper by Pearson and Phelan, and I think that is worth to read. Generally, I have a feeling that it's very worthy to read the papers of Carl Pearson, because they are really sometimes very genuine. And then Edgeworth, Fisher, but it's, I think so this paper in the Royal Statistical Society journal was the one afterwards they decided to call it Fisher information. And classical modern trends, we can find many books, but if you want to have an example of one of the book which was nice for me to read, was Lehmann and Kassela. They have more editions, maybe it's late edition. So what we do actually is we make a score, and if the proper parametric, if we can have a Gaussian random field as a proper parametric model, then we can expect that the variance of the score, if expectation of the score is 0, what is a typical case for models, then this we can call a Fisher information. And there are some aspects which is nice to know, that the Fisher information measures the sensitivity of distributions to variations of parameter in the neighborhood, so it's a local measure of the information. There exists the global measures of informations. There have been works by Igor Vajda, who passed last year, related to the global measure of information. But I will stay with the Fisher, because it is mainly what is used in optimal design. So I was partially impressed and partially shocked that in engineering that the people haven't read, for instance, the statistical or more statistical books regarding the equations, because for instance in Uchinsky already 2005 we can find that the Hessian of the functional, so we can have a very difficult PDEs which will generalize, which will give us the functional. This is observation. You can make a perturbations, and you don't need a lot of time to derive the Hessian. It's probably related to some Russian works, as you told, which I don't know, but I know that we can understand the Fisher information in completely deterministic setup, and I suggest to all engineers to have a look on one of the books related to that, because it's really important that they have this information, because you can do, of course, very many ways how to derive it, with finite element method, with a Galerkin method, and so on. But I mean, the basic is very easy. Am I right? Yeah. So I didn't knew at the time when I was thinking about the thing which I'm relating to the energy. I have known that in this way we can derive some kind of energy from my math studies. So I was thinking about how to understand the Fisher information. So I made a small paper about it in 2005, and later I have found that Luo from China made it in 2002 some similar study. And the thing is, and I think is really interesting to know that if you have a elliptic operator, or you can have any actually any quadratic differential operator, but for sake of simplicity I'm taking the Poisson equation, and you can fix the d-optimal design problem with the correlated errors. As the beginning I will make it opposite from optimal design to the differential equations, not from differential equations to the optimal design. Then you can construct the Dirichlet problem for Poisson equations, so that you have two functions, so that you can solve this in a let us say open set G with a boundary condition, and you can define your Fisher information as energy. At the time I didn't know that it's possible to, so I call it abstract energy, with some discussions with some theoretical physicists that there's no problem for them. And the thing is, so this is the regular case. So you can for each optimal design problem with correlated errors, you can construct this. And the interesting things which is related to the and has some practical application are singularities. So for instance, the one singularity can happen when you have a correlation matrix or covariance matrix which became in some point of your parameter singular. So that means the determinant will be converging to the zero when the parameters will be converging to this point. Then there exists no regular solution of Dirichlet problem. What does it mean? That in probability you will get a blow up of the solution. Just a very simple example what's happening then, and I didn't knew that at the time. I have made just this small study to understand some behavior we have observed with Werner Miller. So imagine that you have a correlation between errors. You have just simply process defined on the interval -1, 1. It will be one-dimensional for sake of simplicity. And you have a correlation of this form, 1 minus the absolute value of difference. It is related to the Gaussian-Slepian process, which have been used a couple of times in statistics by, I mean, since 1950s, but I don't go to the names. And we have just a simple model. That means you have an unknown trend plus this error, and you observe theta plus error. And then imagine that you can observe at the boundary points -1 and 1. What's happening there? The covariance variance matrix at that point will be singular at -1, 1, because you obtain perfectly negative correlation -1. And what does it mean? That in probability the error in -1 is -1 times error in 1. So that means if the error itself is unknown and theta is unknown, then you have measurement in -1 and you have a measurement in 1, but you know that this you can put 1 here in probability, so you have 2 times 2 system with 2 unknown, and you can solve it perfectly. So you have variance 0 estimator, and this is exactly the thing what is happening there. And there is a book by Rozanov and Ibragimov about singular processes, which they call that this Gaussian process is singular. And this is not only, I know that example is toy, but I have found later, or Werner found the paper that the people recognize in some kind of magnetic transitions in MHD experiments, magnetohydrodynamic experiments, that the process can be tuned in a way that itself, in some even stochastic by itself, because we don't know all the complexities, in some phases get the deterministic transitions, and this is so this is a way how we can understand it. So for physicists, it means that you are typically getting a blow-ups of, or you have some qualitative change in the solution of the normally smooth process. So I will relate this later to the applications in imaging. I have found in Tsibako works that they use the thing that you can have a changing correlation to recognize the boundaries of images, and the change of correlation is exactly this. So Werner skipped the discussion on paradoxes, so I can tell we called it paradoxes. Maybe is not a proper name. So this what I made this small example was related to the estimation with variance zero. So you can have various examples. This is the Slepian I did on the table related to the Ibragimov-Rozanov-Bugon singular processes and MHD physics. Of course you can make a perturbation of such a correlation structure, but by properly properly given a singular kernel, you will get a huge class of singular processes. So the second important learning about the stochastic discontinuous time estimation is a so-called Smith paradoxon, where we have a stationary process with a constant mean, and we want to make a naive estimation of this, so we want to utilize all information in each point. And we forgot that correlation can bring a problem of increase of variance. So this estimator won't be optimal, and what you observe, so you can make an empirical version, and you observe the increasing of the variance up to the limit, which is bounded by the variance of this estimator. It's not a proper paradox in a sense that we don't know what's happening, because this is not a best linear ambiguous estimator for this process. So this is just to show that we should be careful with the correlated process. Sometimes on plugging the uncorrelated empirical estimators in a correlated setup. So in some more numbers, so you are bounded by the variance of the utilization of the OR by integral, and for instance for the variance of the utilization of all is like this, and you are this is not the best linear ambiguous estimator. So we can have a loss in efficiency by additional observations in this context. So sometimes it's better to measure less than more. I have seen in financial mathematics by some special financial derivatives, they also observe only till the given time, because afterwards they have a blue of variances. So somehow like intuitive understanding that correlation integrates the variance here. Yes. Yes. I wanted to relate to the Newton. Newton made a great deal in the gravity theory, and I think that the one of the next real contribution was that Einstein, where he considered continuous time space-time. So some of the paradoxes are really related to the using of a continuous time. So if we can believe only in measurable systems, then we can believe that there exists the time which is the minimal time to which our device or our context can go, and outside of this time there is no way to measure anything in a normal sense. there is a criticism of this. The people try to make a continuous time, and there is also a work on the chronom where we believe in a quantum theory of time. So I just want to tell that sometimes, and is not necessarily only a trivial example, you can get a very different behavior of the dependent structure, like a correlation, dependent on how the underlying set looks like. So if it is discrete, if it is continuous, and so on. So if we want to go with the continuous time, we can have as a very seminal, if I don't take a Wiener process itself, so we can take Ornstein-Uhlenbeck process, mean reverting process, as a stationary zero mean Gaussian process given by this stochastic differential equation with a correlation exponential correlation, so it's decreasing. And I want to make a small, there's a small simulation what will happen when I will consider that I'm not able to measure completely the stochasticity of the process. That means that my correlation can have a nugget effect. This is the effect of the so what is observed, there are the trajectories, random walks. So what I'm observing there is just the sum of the realization of the random process, which is Ornstein-Uhlenbeck, and the only change between these trajectories is the how big nugget in the zero is. So I will take by definition at zero the correlation to be 1, and then it can be c times x to the minus parameterized distance, parameter times the distance between the points. So you see that the effect of knowing and not knowing the very small, people call it microergodic effects, can be really huge. For instance, if you are in insurance, then you should have a look on a surplus so that you don't get below the given curve, and then you are risky. So you see that if I change from, this is a classical Ornstein-Uhlenbeck trajectory, and this is with the inputted nugget, and it's increasing, and this is completely down. But this is just a simple white noise. So, but we see that as is different how we treat the time. Is empirical simulation. I can produce some concept how can we work with the processes, and I will tell what we know theoretically about possibilities to have a stationary random field to be discontinuous, and what is it related to. So just for the sake of simplicity, I will discuss just the isotropic stationary process where we make a design in a compact space. A trend parameter is unknown. Covariance structure depends on the parameter R. So it's a specific model where you have a parameterized covariance function with the unknown second parameter R, and there is no interplay. Jesus put interplay in his talk between these two. And these three cases were introduced by Werner, which are important: only trend, only covariance, and both. And the Fisher information matrices we can calculate. If there is no interplay, we have off-diagonal zeros. Yes. So in such a model, what do we know? It's a stationary. There is a result in the London Mathematical Journal. I don't know exactly the name of the journal, but it's probably Royal Society related, by Crum, where he discussed the question: if you have a discontinuous covariance function which is measurable, what can happen? How erratic this kind of function can be? So his result is that you have a decomposition in a way that C sub 0 is a continuous covariance and C sub 1 vanishes Lebesgue almost surely. So that means that if the finance measures its volatilities only with respect to time, that could be a pretty lot of jumps in the correlation when you want to take into account only measurable ones. Measurable ones means, in this sense, measurable with respect to Lebesgue measure sigma algebra functions. So it's clear that what is typically used in geostatistics and all other modelings are mainly the jumps in the zero origin, which we call a nugget. Microergodicity, because of microergodicity, we don't believe that it's possible to measure everything by our model. So there is some microergodic behavior. So if somebody wants to have example, so the most complicated is one-dimensional case, because if you have more than one-dimensional case, then stationarity and measurability already implies that you are continuous except of origin. So geostatisticians are completely right, even in stationary processes, that the only discontinuity is by measuring not macro variability at the origin. But if you are on timeline, which this is a spatio-temporal congress, you can have a infinite many jumps, and it can have a very different behavior of the process, as I have shown here, just for a very trivial simulation like Ornstein-Uhlenbeck mean reverting process with the various nuggets, just discontinuity at the origin. We made the simulations also what happening when you have discontinuities at other places and monotony decreasing covariances. I'm not plotting from time reasons here, but this is showing how big changes can happen. So I'm not able completely, as I have been studied in some recent papers, the people still are not able to completely characterize the Gaussian processes which have discontinuous covariances, but it is related to the singularities in a differential or partial differential equations. So I make a small example, just if you want to see, if you are reading a classical papers like by Zibak, try to use that was a look idea that I will look on Zibak works. He used discontinuity of the covariance when the picture comes to the border. So we have some object, for instance, in the black board, and is white, and when you come to the borders and you want to use, for instance, wavelets, sometimes you get these singularities. So school example of singularities in one-dimensional is this kind of operator. So you have just a time derivative of 80 times the first derivative. So this some elliptical operator on minus 1, 1 except of 0, because that will be my singularity. You have this A is continuous, is positive, and you have a behavior this A t over t powers alpha converges to some constant for t goes 0, and then you take just alpha bigger or equal 1, and you are in the singular Gaussian process, and you have a singular differential equation. So singularities of the Gaussian process are in equivalence with singularities of differential equations, and I didn't find any we don't know completely how to model it. So I would just say that we should know about them before we use our model, because you can get to some problems. So what I wanted to show, one possible way, what I was thinking about maybe last 2 years, what about to make some kind of relaxing of the continuity to discontinuity, and what can we tell about this kind of change? Can we do a design, and how can we characterize? So what I tried is, I have found, since the Ornstein-Uhlenbeck was for me a more close than a Wiener at the beginning. So I have decided how to do it, make a semi-continuous maps of Ornstein-Uhlenbeck covariance in a way that we will take the all non-negative definite functions, such that I'm not taking negative correlations into account, and I'm not taking long-range dependence, because it will be 0 at infinity, and mapping in the distance space can be semi-continuous and non-increasing. So these are the functions which, for instance, can model the nugget as a trivial case. So you have a jump already at the origin, but you can have many other jumps, but in a monotonic way. So as you see, you are getting a maximally discountable set of jumps on positive correlation, and I was thinking what can happen in this way. So of course all continuous, this is just a trivial example, like power exponential matter which are monotonic satisfy, so I can study also this, but these are not of these haven't been at the interest to study the singularities there. So I was thinking which kind of regularity conditions I need so that I can have some properties on this set. And what I'm doing is I'm using a semi-continuity, what means that you have a continuity just that you don't need that your pre-image will be open, but it will be semi-open set. So you accept that you will get a part of the boundary in your image of the open set, of your pre-image of the open set. That's the semi-continuity. So you can have these kind of functions are there, but the class of this function is huge, of course. So then we can represent the processes which have decay in the correlation by the following representation. So it's like Ornstein-Uhlenbeck, just you don't have here simply R times D, but you have a semi-continuous change, a semi-continuous function of D, and no long-range dependence. So there are extremal situations, so you can have non-increasing semi-continuous and maximum countable number of jumps because it's monotonic. And such function has been already used. Computational statistics paper by Werner Miller and Andrei Pazman in 1999. Compactly supported correlated functions. The people try to some of the people use only compactly supported with the continuous, I should admit, but some of them not. So some people use, some not. So Gneiting et al. Have used. So then, of course, smooth functions are there. So now I want to tell some on the motivation why it can be interesting. I'm still not enough far with this. So this was this feasibility of wavelets in multi-resolution representation of images containing edges, where the people realized that both groups, partial differential group and Gaussian processes group, realized that Gaussian processes want to make a jumping correlation at the edge, and partial differential group makes a singularity at the edge. And this is linked. Yes. So just to have a very interesting, so when we are in a Gaussian setup, there is so-called continuity 0-1 Khinchin-Kolmogorov law that if a Gaussian field has continuous covariance, then probability that process is continuous for all times is 0 or 1. Nothing else can happen. So it's very restrictive. So, and what's happening outside of this situation is that you are not having a continuous you don't have simply the continuity of correlation, covariance. So it's a huge set of possible behaviors there. Yes, there is a problem to find a general representation, and so I will just tell what this is about. If somebody interested, he can contact me, but it's very special. It's very special in a way. I was mainly based on the Slovak group of the topologies, Ivan Kupka, who was able to topologize the uniform convergence which I need for some properties. And I'm not further with the thing, but I want to say you can find a topology on the space. So you can forget about the metric when you want to work flexible with the semi-continuous structures. That is the reason why I'm coming to the topology, because with the metric it was for me cumbersome. Maybe it is easier for someone. So I can define a closeness of the class of all processes which have a jumps in the correlation, and that is enough that the target space is regular topological and fully normal topological. Fully normal means that you have a topological version of triangular inequality. So if you have a you can define the triangular inequality by a star of the point. What is the union of all open sets which have this point as an element. I don't go to detail. Just if somebody interested in that. So funny for me thing is that we can still work with the behavior of the Fisher information, because I still have a differentiability with respect to the parameter of interest. I have a semi-continuity only with respect to the distance or of the space. So interesting thing is that since we are Ornstein-Gullenbeck, that was a paper by, with Josef Kiselak in 2008, Statistics of Probability letters, that the equidistant design is de-optimal and optimal, also because Fisher information is just a scalar for a trend parameter. And what changes here is that you can get more flexible designs where you have jumps because of the singularities. Because you can make inverses of the semi-continuous functions which make a deformation of the Ornstein-Gullenbeck. So you can recompute if you know you should know how your deformation looks like to be able to show what is the optimal design. So the way is to estimate the semi-continuity of the covariance function. And I made a couple of numerical experiments when I have taken the data from a semi-continuous covariance, put it, for instance, to the R, and what is happening, so you are getting a strange thing. So instead of this is Ornstein-Gullenbeck exponential decay. And I will introduce a point. I don't want to. If somebody interested, I can show what's happening then with semi-continuous. The typical programs to estimate come to the negative part. So I think that I don't know any routine. So it should be probably developed. So which will recognize the jump in the correlation, which is implemented in some statistical package. So it is not easy to see from the data, because sometimes you get it also for some very erratic data. So I just will tell the general what's happening for Ornstein-Gullenbeck process is that if you have only interest in trend, measure, equidistant design on a compact set. If you are interested also in covariance parameter, then this is giving you in a problem of trade-off, which was observed by Zagorjev Antonini, for instance. They have tried to make a geometric progression designs in the case of Ornstein-Gullenbeck at the same year. We made with Werner Miller the paper on compound designs, which can be sometimes a better solution to this, because you don't need to be completely geometric progressive. That reminds me Radoslav talks, which was really nice to showing how the mappings between the processes change the design equidistant to different designs. But you didn't have correlation parameter of interest. It was just by change of the process. It is actually also open question how we can construct one process from the second one, because what Radoslav told is really amazing, that you can get it simply by knowing which process is it, and you know the equidistant there. So maybe there is a way how to transform from one process to the other process, the design of parameters. Yes, I mean Werner explained completely clear that estimating of only mean and considering that the second moment is completely known is many times not correct. So, and what we observed also with work with Spanish group, Rodriguez Diaz, Maite, and Helmut Walvo made a lot of work there, that we have a big bias of the estimation in our parameter. Yes, for exact designs, other authors, Zagorio, Baldi, Antonini, Harman Stuleter, 2009, 2011, and paper where also prediction has been treated for exact designs in these versions of the one-dimensional processes. Yes, I was still one-dimensional till now. This is just to show if you have Markovianity in a covariance, you can do everything also for a so-called sheets, Wiener sheet, Ornstein-Uhlenbeck sheet. There is a relation between if you have Ornstein-Uhlenbeck sheet of this kind of correlation, so you can obtain it from a Wiener sheet just by this kind of transformation. And actually this was studied by students of Chorgo. Unfortunately he passed, but students still did something on the Gaussian random fields or processes, and we can get for this kind of condition we need to be that we are not overlapping and we need observations without repetitions. We can get also for two-dimensional sheet the covariance matrices, and we can get a similar design. So simply Ornstein-Uhlenbeck looks to be no problematic process because of tuplet structure of the covariance matrix. So this and if we can reconstruct for Ornstein-Uhlenbeck the other designs, it will be really great because we can analytically at least something. I mean theoretical knowledge now, of course, not thinking about just the programming. Yeah, I was thinking what to make that Newton will be happy. So probably we can think about the fractality, and I wanted to I have not enough time to speak about Lipschitzianity, but with Henry so there is a way how to make a topological Lipschitz aggregation operators, and I think that the important thing is there that you can change completely the properties, for instance, on dependent structures where you consider different underlying set. So for instance, you can have a copulas which are fine, and they are very Gaussian Lie copulas, which and you believe your time is continuous, and everybody believes that in the limit I will get a Gaussian copula with the same dependent structure. But I have made I can show if somebody interested, I have made a construction that you have a fractal time, and you will get completely on less optimistic copula for financial markets in the way that your Lipschitzian condition will become much bigger, so you have less control as you thought when you consider continuous time. So that's just yeah, it is for people who are interested. There was a couple of papers which are rather challenging to read on financial times problems with the formula that followed Wall Street by Sam Jones, and that's the last slide. One more thing. People, I have seen that here are people from the community working with the semi-groups. Okay, semi-groups or infinitesimal generators of the operators, or visionized Gaussian processes. So I wanted to just show that in my topological setup, you can still do the continuous transition, which is necessary if you want to prove some, or if you want to use the machinery. So what does it mean? You have simply the two spaces of probability measures, and you will define a Markov kernel. It can be Ornstein-Uhlenbeck kernel, it can be different kind of kernel, by translating of measures with the kernel which satisfy the three classical axioms, and then you can have Markov kernels and the functions so you have a change in the kernel. So this you want to have a continuity in the kernel, otherwise you cannot make an estimation, or it won't be consistent, or you cannot do anything adaptive or sequential because you don't simply you can get anything. We did just it was never published, just by visiting Daniel Hlubinka in Prague, who is expert in Markov transition kernels, that under these conditions you are getting a convergent sequence of the kernel, so you can still do under these topological conditions the continuous Markov fields, not only the exact, that means with a finite number of points. You can do the continuous transition. What is relating to a couple of talks from, I think from Australia, there was a continuous time Markov field. Yes. Thank you for your attention.
We have a strict time limitation. If you want to ask one question, so it's time to do it. I just only want to add that this approximation of this equality of the Hessian to the information matrix is only approximate. So
Yes. Yes. Yes.
Few people use it, so there are.
But I think so it's necessary to highlight it because I mean what I have seen by Heidelberg, so that was a lot of functional analysis behind the.
So, thank you very much once again.